Okay, we'll start today. Today we're going to discuss the marginal spectrum. This I have a confession. For a long time until this year, I don't know how to do the marginal spectrum correctly. I know there's a factor, but I cannot find a factor every time unambiguously. So in the past, I when I made a marginal spectrum comparison with Fourier, I'll always normalize it. By normalize it, I integrate all the area and make the area to be 1. So I make a Fourier spectrum to be 1, Hilbert spectrum to be 1, then I can compare. The reason that this marginal spectrum is the factor, the normalization factor or rectification factor is so complicated, is that we get too many choices. Yeah. Each time I thought I found a factor, then when I use different resolution or different cutoff frequency, the result come out to be totally wrong. So finally, in order to teach this class, I sit down and worked for 2 weeks. I finally find a solution. So I'm going to share this with you. This is brand new, or relatively brand new. I have not even written it up yet. The definition of Hilbert spectrum and the marginal. First, we give the definition, and then we'll show you how to compute it. And then the important thing is the marginal Hilbert spectrum, the relationship between this and the Fourier spectrum. Hilbert spectrum cannot be compared with Fourier because Fourier does not have time coordinate. And if you really want to compare that, you have to use the spectrogram. But the spectrogram depends upon the time resolution. If you really put the time resolution to be so fine, then the frequency is going to be blown up. So you will never be able to make any sensible comparisons. Okay? Then after that, we're going to discuss marginal Hilbert spectrum with different frequency resolution. We know after EMD, we can express X as a function of as a summation of CK. Okay, each of this CK is A times cosine theta. Okay, yeah, this theta time derivative gives us the frequency. Yeah, so this is why we can expand X out into A and omega. Yeah. Now, once you expand that, then if we take square of this, it's a square of all the terms, and we have the square of each term plus 2 times summation CICJ. If our decomposition is really correctly done and nicely done and everything, Ci times Cj should be 0. So we only have CK squared. CK, if we expand it out, is equals to A squared and cosine square theta. Hilbert spectrum is a plot of A, not plot of C. See, each bin at each bin size, we do not put the X value, we put the A value. So that is the first difference we have to notice. Yeah. So Hilbert spectrum, so we define Hilbert spectrum is defined as an energy density distribution in a time frequency space, which is divided into equal size bin of delta T delta omega, with value in each bin designated as A squared. Each bin we put A squared. We did not put the X value because in each bin the X value is still changing. X value is function of time. But the amplitude, it's A squared at the proper time and the proper instantaneous frequency. So this is the definition of Hilbert spectrum. And the definition was given in my original paper, and I realized that the spectrum is not normalized. In other words, it's not a density. So in my original paper, I say this spectrum is a probabilistic spectrum, which is true. But I've never given a more clear, more rigorous definition than that. Yeah. Because at that time, the spectrum is not given as energy density. If we give it energy density, then we can make comparison, because Fourier spectrum is in terms of energy density. Other than energy spectrum, we can also do amplitude spectrum. In other words, instead of compute A squared, we just simply put A, the amplitude. Then once I start to study this, I find that in the past, many of the results I got actually is amplitude spectrum, because I forgot some of the programs that the programmer written for me actually is not in terms of energy. So if we change this energy to amplitude, and everything else is the same. The energy amplitude spectrum can also be defined, and defined rigorously. And therefore you see that we divide time and frequency space into equal bin, and then you just look for your EMD components, and each component, if it's fall within one bin, we put that value there, and that value is delta omega delta t, and we put it as Sij. Okay, so why we have to define the bin? At the beginning of developing this, the computer is of very limited power. If we do not divide in bin, we just keep plotting this x time as frequency. You get one line after another. Each EMD will give you one line, and that one line, it's very difficult for you to make any average, make any statistic sense. And if you divide into bin, is another advantage of dividing into the bin is that you can control for different EMDs. You can control how many, the size of the spectrum. Then you can do statistics. So at the very beginning, we decided to use the bin to regulate this spectral energy. Once we divide into bin, of course, then each bin, so how many points fall into the bin is actually the spectral density. Now just imagine, if I use this as a bin, then this one has 3 point, 2 point, 1 point, no point. Okay. If I increase my bin size, for example, if I increase my bin size to this, then that one bin will have all the points. So the energy will be very, very high. So depends upon the different bin size, the energy point will be very different. Yeah. But if you divide into the energy density, however, then the large and small, of course, will be different. But the difference is that this density, the large one will be the average of the small, not the sum of the small. So that's the difference. If we do not talk about the density, then we talk about the sum. But even that, there's still, in the Hilbert spectrum, there's still elements of sum in it. Here we have, on each bin size, in each bin size we have numbers. If we divide this even further, then each bin size, the total energy in each bin size will be even smaller. Okay, and a lot of empty spaces will appear. So the final spectrum really depends critically on the size of your bin. And so currently the spectrum is defined in terms of density, is not defined in terms of density. So the program that I give you, still it's not density, it's just the sum. Okay, so the value is simply the energy value at a particular bin. So define the spectrum in terms of density only define density, we can make comparison with Fourier. Okay? So therefore, the value in each beam should be Aij divided by delta t times delta omega for amplitude spectrum, and A squared divided by T omega for energy spectrum. Yeah. So once you evaluate this in the density, then you'll find that then we can also define Hilbert spectrum as integral of time. Yeah. This integral of time, simple as it is, actually evaluation becomes very complicated because the beam size is free. We can choose the beam size every time. We can zoom in. We don't have to use the whole spectrum range. The freedom of our choice of frequency time resolution, however, makes the marginal spectrum evaluation much more complicated. Yeah, it's so complicated that I get totally confused for a long time. Yeah, so we need to define it rigorously so that we can make comparison. Now, the computed Hilbert spectrum is that time is designated as T0, the beginning time, and delta T to delta T until the final T. Yeah, omega is same thing, omega 0 all the way to omega 1. This T0 and T1 is totally free for us to choose. If we have spectrum, if we have data for total 0 to capital T, yeah, the only requirement is that T0 and T1 to reside within this interval. If you're outside the interval, of course, there's no value. As long as inside, it's fine. For example, we have data from 0 to 100 seconds, but I only want to see from 10 to 20 seconds. We can do it in the Hilbert spectrum. We can select which time range we want to see. And this time delta t also can be any value. You don't have to be the sampling step, but it cannot be smaller than the sampling step. Yeah. So all of this we can select. And once we select this, of course, that gives us a lot of freedom. And how about the frequency limitation? The frequency limitation is that the frequency scale in Fourier spectrum, the frequency scale is limited by delta t and capital T. In Fourier spectrum, you have no choice. Yeah, if the total length is capital T, then your frequency step is 1 over capital T. Yeah, that's not changeable. And also, the highest frequency that you can ever resolve is 2 over delta T. That's the Nyquist. If you select your sampling rate, and then the highest frequency resolution is determined. Yeah. Not only that, the frequency resolution is also determined. So that's Fourier, and that's why it's so easy to normalize Fourier, because you have your total time, you have your sampling rate, then the spectrum is fixed. Now in Hilbert spectrum, however, the Nyquist is a problem. Here we have 2 times 1 over delta t. Yeah, 2 over delta t. That's the Nyquist frequency of Fourier. In Hilbert spectrum, the highest frequency, if probably will not get there, because if we want to evaluate the frequency, we take a derivative, and if you have 2 over delta t, that means that particular wave has only 2 points. For 2 points, you compute the phase and you take a derivative, and that phase and derivative may not be very meaningful. So what we hear, I have always used 4 times the delta t as frequency. 4 times delta t means our frequency, Nyquist frequency is much lower. We need a 4 points to define rather than 2 points to define. So we're using 4 times to define, our frequency is much lower. Fourier can go higher in Nyquist. However, the highest frequency that you can get from the Hilbert spectrum sometimes surprise you. For example, when we take a derivative, if you have a singular point, that at the point of derivative, that value can be very high. So local value can be very high, but that is not limited by the Nyquist because it's limited by the local slope of the phase value, phase function. So we are somehow limited in the Nyquist, but this Nyquist is just regular Nyquist, and occasionally you may have a point that may even exceed that. So Hilbert spectrum, then the definition of Hilbert spectrum is that for any del omega at any arbitrary j, then we have summation a square for all the I and j, and this a square should be divided by del t del omega. That gives us the density within that beam. So the Hilbert spectrum Sij definition is summation I and j a square and j square. In the past, I have never put this factor in. This is a new factor. We have to consider this. So the marginal spectrum is this spectrum times delta t and integrate. Okay, so we have delta t. This is given as a density times delta t. So so this delta t and delta t cancel. So the marginal spectrum t is implicit. How many time interval you put it in is not going to influence marginal spectrum. Yeah, because marginal spectrum, this t and this t cancel. Marginal spectrum only depends on delta omega. So if you have a goal only to calculate marginal spectrum, you can put this delta t, whatever value you want. Yeah, in calculate Hilbert spectrum. Now, the total energy is interesting. The total energy is E times Sij, which is the evaluate of the Hilbert spectrum as defined here, times delta t times delta omega, sum over all j's and all omegas. And that's summation of marginal spectrum over del omega. So this del omega and this delta t times that give you us marginal spectrum. Marginal spectrum with respect to omega is omega cancel. So finally summation is a square. It's amplitude square. So our total energy is amplitude square. And amplitude square equal to 2 times x square. Why? Because x square equal to a square, x equal to a cosine theta. So x square equal to a square cosine square theta. When cosine square average is half. So if we use a, that will be twice the x. So therefore, the energy is not averaged a square. A square bar as in Fourier. Fourier spectrum by Wiener-Khinchin theory always give you total energy density, not total energy. Yeah, it's give you RMS value. Here we give you the square sum. Yeah, that's the difference. The spectrum output and the definition, because of the definition, the spectral output is very, very different. our computer is, excuse me, my computer is not compatible with yours. This becomes square. Actually, that's a dot multiply. Yeah. Anyway, so now we see the total energy in Hilbert spectrum is summation of the marginal spectrum, is also double summation of Sij, and this double summation of Sij is a square equal to the summation of x squared. Now if we take x squared over here, if we compute energy, regularly we compute energy, we use x squared. So energy defined as x squared equal to summation Cn squared. So this Cn squared is equal to summation Cn parenthesis square, because there's no cross product term, so this is equal to Cn square. So you compare these two, so E is only half of EH, because E is defined as summation x squared. It's not 2x squared. So this is this is half of it, and because it's half it, this is Cij. Therefore, a squared equal to 1/2 c squared Cn squared. So there, even if you sum of all the energy and you divide it by all the total numbers, and there's still a factor of 2 difference there. So the Hilbert spectrum definition, once we go through the algebra, you will find that it's a little bit different from the Hilbert spectrum. So now we see further. The definition of Hilbert's Fourier spectrum is x bar. X bar equal to s omega d omega. S omega d omega. Del omega is 1/t. That's Fourier spectrum definition. Now, x bar, however, equal to x squared bar equal to x squared divided by the total number of points. If you have, you keep adding it, and the average is divided by the total amount of points that you put it in. So there is a factor n. N is the total number of data points. Depends upon how many data points, and that determines this n. Okay? Now therefore, x bar, x squared, if this is the definition of x mean, so x squared equal to n times x mean. And n times x mean equal to n times the Fourier spectrum. But this del omega is 1/t, so this spectrum come out as t, and and this n out. So this n/t, it's the spectrum. And this spectrum is about half of the amplitude of the amplitude. Therefore, summation of a squared equal to 2 times n/t summation Fourier spectrum. So here we have a big factor here. Depends upon how many points, depends upon what's your frequency, total time and total number. This n/t, however, is actually the sampling rate. So it depends upon sampling rate. Yeah. n/t, the total number of time, how many numbers you got over how many times you got. This is 2 times the sampling rate. So when you compare Fourier spectrum with the Hilbert spectrum, it turns out to be the sampling rate becomes important. Yeah. So that is something which I did not fully appreciate. So I tried to find the normalized factor, and it's strangely many people use Hilbert spectrum. Nobody actually look into this, yeah, and because it's so, this is not the end of the story yet. We'll keep on going. I want to get you guys totally confused. Yeah. Now, what if my marginal spectrum is a different resolution? With a different resolution, we have this already. This is the definition. Now, if we have arbitrary resolution, and arbitrary resolution including arbitrary cutoff frequency. I don't, when I do Hilbert spectrum, I don't have to go all the way to Nyquist. I usually look at, when I think, let's say for example, if I look at the length of day. Length of day has 14,000 data points. Yeah, and the data rate is 1 per day. Yeah, but I know this 1 per day. There's no information, so I never go all the way to 1 per day. Yeah, so I can arbitrarily take different time resolution and different different frequency resolution. If I take a different frequency resolution, I'll have omega. And so there is another factor of del omega A that depends upon my frequency resolution, compared with the full frequency resolution that the Fourier will give. So a factor of omega over omega A is hanging there. So if this omega A cancel that omega A, you get 1 over omega. And then that is what the Fourier spectrum will actually compute. So there's many layers of different factors, and these different factors all because of the freedom we got. So you get the freedom is not free. The freedom means that each time you compute the different resolution, you will have to keep track of what you use. And with that, what you use, then you can finally revert it back to Fourier, because Fourier has a fixed del omega and fixed, everything's fixed. So the spectrum density depends upon the beam size. That's reasonable, right? Because if I have very coarse beam size, then each beam size will have many, many points. So I have more points of the total energy. But divided by density, so this beam size depends on both temporal and frequency resolution. But for marginal frequency spectrum, the temporal resolution is implicit. We have seen that the temporal, when you define marginal frequency spectrum, you integrate time out. So if you have a large beam size, you multiply it by delta t, and that delta t cancel your beam size. So for marginal spectrum, the temporal resolution is not important at all. Yeah, it's canceled out. For instantaneous energy density, if you try to compute, see, we always compute marginal spectrum as function of frequency. But what if you try to compute energy as function of time? In that case, then the frequency resolution, for instantaneous frequency, the frequency resolution is, well, here is implicit. The frequency resolution becomes not important. If you calculate instantaneous, this is a typo here. Not frequency assume instantaneous value, not mean. So it's not limited by the Nyquist. Yeah, and we can zoom the spectrum to any temporal and frequency location, and that is, I think, one of the properties in the Hilbert spectrum that people do not realize. It's really a magnified glass that you can look into one location with all your resolution. You can, but of course the time cannot be smaller than del t. But other than that, the frequency is continuous, but almost continuous. Yeah. So this is the summary of that. So the Fourier versus Fourier versus Hilbert spectrum is the adaptive base, and we have time frequency presentation, and the physical meaning. We have physical meaning for frequency at both high and low frequency range. Fourier frequency in the high frequency range, you run into the probability, or actually the certainty of getting harmonics. And here in the Hilbert spectrum, you don't have harmonics to worry about. So the frequency has physical meaning. And the resolution of frequency is adjustable, not like Fourier is fixed. And we have zoom capacity and marginal spectrum for frequency and for time we can find the marginal spectrum for frequency and marginal spectrum for time. So you can integrate over all the time, you get a frequency marginal. Integrate all the frequency, you get a time marginal. So we have this freedom of choice. Now, example, to study white noise. What really makes me think very, very hard to do this is one PhD dissertation done at Southampton University. This Southampton University, the student actually is not from math department, it's from chemistry department. The chemistry department people is trying to study protein structure to make new drugs, new medicines. The protein structure, they study that, and the student, Gilhill, he tried one thing which is very puzzling. He put a white noise in, and he computed the spectrum, found the spectrum is not flat. And they started to scratch their heads. So the spectrum, white spectrum should be white. How come the Hilbert spectrum, marginal spectrum, white spectrum is not white? So they keep on trying to normalize it, but never succeeded. So finally they developed a empirical law. That empirical law, however, is not applied to every case. It's just applied to that particular case. This becomes a very annoying problem, and that was documented in the PhD dissertation. I read the dissertation. I feel that, of course, that kind of result will never be able to be published. If it's published, then it'll give a very bad name to Hilbert spectral analysis. So that was a couple of years ago. So ever since that time, I started to try to look for it. It turns out, if you do it right as I prescribe, it will be okay. So here is a white noise. It's a standard deviation of 0.2, and white noise that I generate is from 0 to this mean value is over here. This is not zero mean. Okay, non-zero mean. So when I do a Fourier spectrum, Fourier power after I take out the mean, I detrend it. It becomes this. If you do not detrend it, you see this is a very flat, relatively flat. And if I do IMF of that, and I plot the spectrum without the detrend, you see Fourier spectrum has a tilt. This tilt is not because of the spectrum is not flat. It's because you have a DC component. The last component is DC because its average is non-zero. See, this is a non-zero mean DC component. Yeah. And this is the blue one is a Fourier. The red one is Hilbert. The Hilbert is also very complete, very flat until it comes to the end. Yeah. Remember, this is because that we have that. I should take this mean out, but when I compute the data, I find it's non-zero mean. I just let it go. Yeah. Now, I have a Fourier. This dotted line is Fourier. All the other lines are Hilbert spectrum. This Hilbert spectrum has different resolution, different beam size. Yeah, the beam size, the smaller the beam size, the higher the value. Because here is totally unnormalized. If your beam size is very big, then each beam has a lot of energy. So when you add up, it becomes very high. And as your beam size decrease to all the way to almost near the Fourier, then the the density approach to Fourier. Yeah. So each of this actually has the influence of beam size. See, here is I have 800 beam, 600 beam, 500, 300, 100, 50, 20, 10. I have all kinds of beam size, and that creates all kinds of Hilbert spectrum. And that was what had bothered me. I can never bring all this together properly, yeah, in the past. And if, however, I multiply the factor, the total number has 1,000 data points. So if I multiply this by 100, multiply this by 500, 150, 20, and so on, then I was able to bring this all the Hilbert spectrum into this one line. Yeah. So, in other words, Hilbert spectrum can be properly scaled if you know your beam size. Yeah. If you know your total number of data. So this is the normalized Hilbert spectrum. And this is, of course, the Hilbert spectrum is del F equal to 10, 20, 50, and 8,000 divided by 800 divided by 1,000. 1,000 is the total number of data points. 500 is the Fourier resolution. Yeah, we can do all the way to 1,000 time beams, but we cannot do more. So so if you have beam size, effective beam size, if you have a beam size of 50, beam size of 250, beam size of 500, if it's a factor of all without any normalization factor equal to 1, you have different lines. Yeah. Now, if, however, if you multiply that 50, the ratio of this is 10. If you multiply this by 0.1, multiply this by 0.5, half 1, then everything falls together. So the beam size is linearly proportional to the density. Yeah. Now we can have all the spectrum all reduced to the same level. This is very different. This at the beginning is very confusing to me because Fourier spectrum, it's always normalized. If you use window, the window will normalize it for you actually. And if you have zero mean data, we get RMF. You can see that this is the Fourier spectrum. The Fourier spectrum of all the data, Fourier spectrum, different window and different window. This is the nice part of the Fourier spectrum. If you use different window, it's already normalized. The normalization is so easy and it's automatically done. If you plot the Fourier spectrum, it's always that line. Yeah, and then the integral. You may ask, if the different level has all different lines, how come it's all at the same level? It's because you plot on the same resolution scale. If you plot the different resolution scale, they will be different because the integral, the total energy, depends upon the value multiplied by del t. Yeah, this value is the same, but this delta omega is large. But delta omega is large, but this has a much fewer points than this. For example, 250, I have a point here, a point here, but I don't have a point over there. So 512 has an extra point, even though the beam size is half, but it has one extra point, so it's made up with that. And the same token, if you have 1024 and same data points over here, then you will have 2 extra points, 3 extra points. So Fourier spectrum, by its definition, it comes out always normalized. Yeah. And this is the nice part of it. The resolution, by choosing different windows, the resolution will change. For example, this line is much smoother than that line, and even more smoother than this line. And this line, it's rugged because I have more resolution. Now, we look at the Fourier spectrum with all kinds of different windows. You can have a window so long and has a window so short. They always give you the same line. The Fourier spectrum plot out always hug the same line. And that's why when I was at the beginning, I was very puzzled. This is how come Fourier can always get in one line, because Fourier has already normalized it already. Now in here is the Hilbert spectrum with marginal Hilbert spectrum with all different resolution. If you put the proper normalization, you will also get the same line. It's the same way. But this proper resolution takes some of the doing, like what I said at the beginning. And one line is very different. If, however, you decide to do amplitude rather than amplitude square, and that will be very different from Fourier. Not only that, it actually has a slope. So the amplitude spectrum and the energy spectrum are very different things. You have to be very, very careful that if you plot amplitude spectrum, try to compare with Fourier. It is no comparison. Yeah, Fourier is energy spectrum. Yeah, and if we use earthquake data, and we can decompose it into adding 0.2, adding 0.1, adding not add any noise at all. They are all different decomposition. But if you plot the spectrum, and plot the spectrum with, say, Fourier with the total data points, you get this. And Hilbert with 7,000 resolution, you get this. So the two, when I first plot this, the two will never agree. Yeah, even though the Fourier, even I put all the data points in there, the Fourier give you 7,000 data points, only 7,000 data points. And if I put 7,000 data points in here, I still will not agree with that. Why? It's very simple. This is the total energy. This is the energy density. So the difference between these two is that this is a factor of capital N there. Yeah. But capital N, but you think the capital is the total capital N? No. It's also the total time. This capital N over capital T multiplied by 2. So the difference between this and this is actually twice the sampling rate. Sampling rate is 200, so here is the difference is about 400. Yeah. So if you multiply that factor is 14,000 divided by 70, this is total time. That's a factor. You multiply Fourier by that factor, but this is twice of the Fourier. So you multiply this by 1/2, the two agree. So this is actually the sampling rate, and this is the factor 2. So if you multiply Fourier by twice the sampling rate, you'll get the perfect agreement. So that is the key of the normalization. If every time you plot the spectrum, you say that if I have 1,000 data points, I use 500 frequency beam. If I use 500 frequency beam, then I multiply 2 and the frequency sampling rate, you would have a perfect agreement with Hilbert. We have a perfect agreement with Fourier. So after we have everything boiled down, it's just that simple factor is that the sampling rate, this total number divided by total time, and a factor of 2. That's it. So once you went through all the number and put every number step by step, you boil down to this little factor. This little factor is extremely simple. It involves the total number and the total time. You can combine that with the sampling rate, and that's it. And Hilbert spectrum, once we get a Hilbert spectrum, we can smooth it. And here, I smooth the Hilbert spectrum by 7 and 7 Laplacian filter to smooth it. I smooth it three times. 3 times 7 by 7. So the Hilbert spectrum was, compare this one with that one. See this here, it's smoothed. Once it's smoothed, and this becomes much cleaner, and then you make a comparison that the smooth, the spatial smooth, not the spatial, the time frequency smooth in the Hilbert spectrum does not influence the power level, the total energy level of the spectrum. Yeah. It only smooths out this curve a little bit. If you look at this curve still have the same number of points, but this number of points has been smoothed not only in frequency but also in time to give you this spectrum. So you see here's a peak and there's another secondary peak. You can see it clearly. But that secondary peak, whoops. That secondary peak is not very clear here. It's all in this big band of noise number. So if we averaged, we would see it cleaner. Now here, I demonstrate again. If I use 7,000, that's this point, use half of that, use 1/5 of that, and eventually I use only 70. You see the spectrum difference? If I use 70, it's way above that. It's way above it. And this is giving the frequency band. Can we always use 70 frequency beam? Depends upon how careful how detailed you want to have the resolution in time. Yeah, 7,000. If this is 14,000 data points. If you use also 14,000 time step, that becomes a huge matrix. Yeah, sometimes use my computer was locked up. Yeah, so this depends upon how many data points that resolution you want to get here. Now here, the reason I give you this detailed discussion is that if you really want to have very good frequency resolution, you can forget about the time resolution, because time resolution is not important if you want to compute the marginal spectrum. So the time resolution, you can do 2 beams, you can do 10 beams. Yeah. So don't look at the Hilbert spectrum as time frequency. You can put all your resolution in frequency. You will get this detailed frequency resolution, and that's feasible. Yeah. In the past, I did not dare to do that. I always put some time resolution in it. Once you put time resolution, that with your computer cost, computer capacity, you are limited in this frequency bin. Yeah. So if you want to have a good frequency resolution, just put all your resolution in frequency, sacrifice the time. And the time you can just take very crude, 3 bins or 10 bins or very limited bin. So if you put the 10 bins, and that equals to 700 horizontal bin and 100 time bin. That's nothing. Yeah. So, but if you use different frequency bin, you obviously will give different values. But this is very easy to recognize, rectify, because see, this 70 versus this 7,000 is a factor of 100. So this and that value is about 100, 10 to the 2. So if you divide this by 10 to the 2, you bring it down to here. Yeah. Divide this by this one. This is 700. This is 3,500, and the factor of 2. You divide this by 2, you bring it back down. Yeah. So it's the factor. Once you think it out, it's really not that complicated, but it's just the initial freedom give you this too many choice sometimes confuse you. Yeah. So this you have a factor of 100, factor of 50, factor of 10, 2, and 1. That will give you back to this. But then, if we want to bring this to the Fourier, we still need 2 times the sampling rate. The sampling rate is 200, Fourier is 2 times 200 is 400. So that brings everything together. So now you have the total package. Yeah. If you set the resolution to 100, if you set this is the Nyquist. This is the Nyquist of Fourier. So if we follow Fourier, you put up Nyquist at 100, then the computation is so simple. Yeah, it's 2 times the sampling rate. We immediately bring it back to everything is normalized. Yeah. So the difference from EMD and EEMD, this is EMD, this is different stoppage criteria I use for EMD without that. And we see a little bit different. I do not know why is this. It's perhaps because of the mode mixing or whatever. I have to look into this a little bit more. But I just want to point it out that by different stoppage criteria, you do not have large differences. But this difference, there is a systematic difference between EMD and EEMD. Yeah, I just want to point out this. At this time, I thought I have the problem solved. Then it comes to the problem zooming. Yeah. I have already set all the frequency to the Nyquist frequency. Then we have a very simple formula. It's 2 times the sampling rate. Should be normalize it. But what if I want to zoom? By zoom, you see, I look at the spectrum and I say that, yeah, between 10 and 100, it's all noise. Why should I spend all the resolution, all the computer power to compute the frequency above 10? And in the earthquake, frequency above 10 is probably not that interesting anymore, especially for high-rise building. So if I set this factor here, I said, no, I don't want to look at beyond 10. What will happen? This is the difference. If I use beam size of 7,000 and using factor 1, I get here, this spectrum is different from the Fourier spectrum. Okay, but if I realize that it's 10 to 100 is a factor of 10. Yeah, because my beam size now has a factor of 10 difference. So if I multiply a factor of 10, I immediately bring that down to here. Why we have this? Because you've put 7,000 resolution all in very short period. So your frequency resolution is much, much finer. Yeah. So now I can bring this back down here. And then I will get a spectrum which is pretty close, very close to the Hilbert, to the Fourier. So now we see that if you start to have zooming, and you want to use zoom, you will have another factor to contend with. Yeah, and that factor is the total ratio of the beam size, del omega. That is the omega A over del omega. Yeah, that we pointed out before. So this show you that even with zoom, you can bring it back down. And now we can have 700, 7,000, and the factor 1 is no good, and it's 700 with 7,000 is already a factor of 10, and with zooming is another factor of 10. So you multiply a factor of 100, you bring that back down here. That will track this spectrum perfect. Yeah. So with 700 beam size, beams, so you have a much smoother point than the 7,000. So each point represents almost 10 points. So you have 10 points average. So, but you can have a very nice spectrum. So sometimes, if you have a very fine resolution, the fine resolution actually gives you so much detail, and you will get such a wide band, you will not be able to see what's the variation in between. Okay. A lot of time, using lesser frequency band can actually get you a cleaner spectrum, because small beam, small number of beam already implied average. And this beam size 700 with 7,000, that implies 10-point average. Yeah. So if you do 10-point average of this, you probably get that. So when you compute the spectrum, you have also realized that with finer resolution, you get more detailed reading. And more detailed reading depends upon how you plot it, and sometimes you may not even see the details. The details become buried in this large fluctuation. Yeah. And in that case, using some number of using smaller number of beam size actually get your result cleaner. The alternative, of course, is go average, but this is average already. Small beam size means already over the beam that you averaged. So, and if you plot amplitude spectrum, however, this is a Fourier power spectrum, this is a Hilbert amplitude spectrum. Amplitude spectrum would be very different. Yeah. Now, ensemble. So Fourier marginal spectrum, this is raw data, as we pointed out before. And we can normalize it. And if we use various window, then we have various different kind of resolution as before. See, this is actually the original spectrum with up to 100 hertz. Yeah. And you look at 10 hertz, you get all this little beam. And you look at 10 hertz, you get even more beam size. It all depends upon your time and frequency resolution. So Fourier analysis, time frequency is fixed. In Hilbert, there's infinitely many games they can play. Depends upon whether you want to see the frequency resolution or you want to see the time resolution. You can play this kind of game and actually get this coarser and coarser. So with a different beam size, we can normalize it just like I explained it before. Yeah. And zoom effect is the same thing. We can zoom it back to the beam size. Yeah. These are all the different examples that I worked out. Now finally we get to delta function. Delta function should give us a flat spectrum. And will Hilbert give us a spectrum, flat spectrum? The answer is yes. The delta function looks like this. You expand it out in delta, you get this. You get this different component. By the way, I have never been able to get a very good IMF for delta function. This looks great, but the orthogonality property is very poor. And if you try to decompose delta function, the normalization are not that. There's lots of leakage, in other words. Yeah. So if you plot the delta function, you have with different beam size, you get all different spectrum shape. Looks like this. Yeah. This is a less beam size. This is more beam size. And when you plot the spectrum, this is only 1,000 data points. You find that the spectrum this is a horizontal line. You find the spectrum is very close to the horizontal line with some fluctuation. This fluctuation, most of the fluctuation, are actually caused by leakage. Yeah. If you add up, the total energy will not be 1. This is something which I cannot totally resolve. Yeah. However, if you add everything together, it's the delta function. But the square of that is not 1. Yeah. And that gives us a little bit humped up. But this humped up does not influence the general flat spectrum that you will get from the Hilbert spectrum. Yeah. This is the Fourier spectrum. It's a perfect flat line. Yeah. Fourier energy spectrum. So summary, Hilbert spectrum are time frequency resolution. Why we spend so much time talk about marginal spectrum? Because there are a lot of people cannot give up Fourier totally. They always want to make some comparison to make themselves comfortable. So they say, yeah, I do have this. Yeah. So, but Hilbert spectrum actually, I usually look at the Hilbert spectrum, not at the marginal spectrum. I always use the Hilbert spectrum at time frequency resolution. But most of the time I compute the marginal spectrum just to show people that here's what you got. If you are familiar with Fourier, this is what you can compare. The marginal spectrum can have various resolution and zoom capacity, and that's what confused me. I believe it confused to many other people too. Yeah. And this freedom gives us so many variables that if you don't think very clearly, you may get totally confused. The Hilbert marginal spectrum could make smooth without losing resolution. Here, this statement is not technically not totally correct. Without losing resolution means I still have the same number of points in frequency, yeah, but it's smoothed. Many other smooth, you may lose number of points, but this statement need to be modified. Okay. Another marginal Hilbert spectrum quantity is the time-energy distribution. You have the time-energy distribution, and then you can compare with the Fourier. Yeah. But that time-frequency-energy distribution, if you think in terms of density, then because of the zoom and because of the various resolution, it adds up two dimensions for you to play with the factors. And you have to be very, very careful when you compare with the Fourier spectrum. It's not automatic that one will fall on top of each other. Yeah. You need all these normalizing factors. Yeah. For a long time, the Hilbert marginal spectrum is not defined absolutely. That's my fault, because I never sit down to work out all these little things. If I sit down, I might resolve this problem at the very beginning. But at the very beginning, I get distracted by such excitement of looking at the different time frequency analysis. I never pay attention to this. The energy and amplitude spectrum were not clearly compared. They are totally different things. You cannot compare the two. Yeah. I think I made a mistake in the past by using amplitude spectrum as energy spectrum. So you have to be very, very careful on that. The clear conversion factor are given to make a comparison between marginal Hilbert spectrum and Fourier spectrum. So once we work out the conversion factors, then you'll still be able to do it. In fact, even after I work this out, this has not been part of my system yet. So a lot of time, in the haste of computation, I still made mistakes, but of the conversion factors. Yeah. But this conversion factor is very clear. You can work out, and this conversion factor is provided for different resolution and also for zoom. Yeah. In most cases, the marginal spectrum is very similar to Fourier spectrum. When you integrate all the time out, even though I do not intend it to be Fourier spectrum, a lot of time they look alike. The difference, however, is due to nonlinear. If you have a nonlinear signal, there will not be the difference. Okay, because we do not have harmonics. Yeah. So other than that, the data could look very, very, the Fourier spectrum and the marginal Hilbert spectrum could look very similar. I think that's the end of this lecture. This whole lecture represents the work of the last couple months of finding out the factors for the spectrum. Now the spectrum is clear. So to show that you really learn how to do spectrum, pick any data, a earthquake or whatever, do a few spectrum with different resolution, try to normalize it. Okay? Just to demonstrate that you understand that. That's our homework number 2. And that's extra for you because the Japanese won't have this. They have never listened to this, so they won't have this homework. And so when you do the homework, please include this. So have 2 homeworks. Okay? One is that the sensitivity study. The second is the Hilbert spectrum. And if you do not have any data, generate a random number, 1,000 points. And you can compare your result with my result. That I use 1,000 data points. And when you use data points, make sure to take the mean out, zero mean. Zero mean, okay? Use a zero mean. If you do not have any data that you like, use zero mean random noise, 1,000 points. To calculate the spectrum with different resolution, try to normalize it. All right? And that, if you can do that, then it means you learn this lesson well. And once you normalize it, compare with the Fourier spectrum. Okay. put the Fourier spectrum there to see how it looks. If you generate random noise, everyone's result will be different because you will never generate the same random noise. So it cannot be all the same. Yeah, everyone have a slightly different answer. That will be all right. So I think I talk very fast. I'm 20 minutes ahead of the time. So the floor is open for question. Anybody has any question? Yeah, go ahead. Sure.
请问一下老师，就是老师说看什么验证啊？
嗯哼。
验证的话是罗雷卡加的noise，
嗯哼。
还有验证的是
嗯哼。
然后再 noise 加罗雷卡再分组。
嗯哼。
其实我们上个100的话是把100面加起来。
嗯哼。嗯哼。
那请问它是用
median。中位数你也可以做中位数。In fact, 中位数有的时候 the average is not fair. I will answer in English, okay? The question is, EEMD, we have to do many ensembles. First realization, second realization, then finally we average, then get the EEMD result. The question is, can we, instead of use mean, but use median? Okay, mean and median has very different meaning. Yeah, but if the sample is fair, if the sample is not biased, okay, mean and median should be very close. Okay, but if you have outliers, then it will be different. Outlier means you have suddenly have a very large value. Yeah, to use median is just to exclude the extremely large value. Yeah. In most of the time, if you have same extreme large positive and negative, then the median and the mean should be extremely close. Yeah. Oh well, then the median will not help you. The second question is that you use IMF, EMD, then you add noise. Then every time you get different components. Okay, this two-way to resolve that. I'm sorry I did not explain it in the class. I thought I did. Anyway, there are two ways to resolve that. The first way is Dr. Wu's way. Dr. Wu's way is I will fix the number of shifting, and I will fix the number of IMF. Yeah. A fixed number of IMF is that I only want 10 IMF. Beyond 10, forget it. Okay. So I average is 10. I'll put it in there. So then I will get it. But the other way is my way. I will expand it out. Like if I want 100 ensemble, maybe I'll calculate 150 cases. But if I get 100 value that all have the same number of IMF, then I'll average those and throw away all the other out. And turns out that my program was written in a way that I would do first 10 times to see which one has the potential, and you just keep on doing that until the first one reach 100, then I stop. When you look in the other cases, usually they are small, relatively small. Now what you suggest is maybe a third way to do it. The third way is that if I have different IMF, okay, so this different number of IMF, if I include it, will be outliers. So if I threw it away, then I will still get a medium number. Medium number means that excluding the outlier. It's a good suggestion. Why don't you do it as an extra? Just to satisfy yourself. You do a average way as before, and you do a medium, and compare the two. Okay? Do that as extra. That is a good suggestion. Any other questions? Yeah, sure.
就是之前我有看老师的内容，就是老师说今天还没回答到就是取出来用一个意念力盘之后，它的诺结就这个发手。
嗯哼，嗯哼。你说它的 noise level 是 square root of n， 这个是 that's statistics。If you have statistics average, if you have average n times average, because of the cancellation, the RMS will be square root n divided by the original RMS. It pick up any statistical book, you see the proof of that. Okay. Okay. Yeah.
So you say that the marginal Hilbert spectra and the Fourier spectra, except for La Nina and the harmonics, should be identical.
Not identical, should be very similar.
Very similar.
Uh-huh.
Can we announce that because the La Nina energy is taken as harmonics being zero to the high frequency.
High frequency, yeah.
So Fourier result is overestimated in the low frequency.
No, it's underestimated because some of the energy has been put in the high frequency, so Fourier will be lower. See,
but a lot of people are using Fourier finding some mode frequency.
Uh-huh. But that mode frequency, it's just one of the frequency being. So if a structure has mode, the oscillation has to be very, very simple. So you have mode lines. If it's a very complicated mode, it's totally random vibration, perhaps you will never find a mode. Like for example, in building, you may find a mode because building, the oscillation, it may have some jitter, but the oscillation, basic oscillation, is very simple. Only simple oscillation has mode. Earthquake will never find mode. Yeah. Okay. No more questions? Oh, okay. Yeah.
So we are looking at the spectrum of each component.
Yeah.
Then we see the compared Fourier.
Uh-huh.
If this curve is drawn as so-called marginal, there's a marginal is a combination of all the.
Exactly. All the modes. All the modes. All the modes except the last one. Usually. The last one usually it's trend, and the trend usually may not have zero mean because your data may not have zero mean. So the last trend I usually exclude. Other than that, everything's in there.
So it's kind of you want to prove that all components combined will almost equal to
Fourier.
Yeah.
Yeah. Almost equal to Fourier if the process is linear stationary. If the process is non-linear, non-stationary, it will not be the same. Non-linear, especially non-linear, you have harmonics. It will never be the same. For example, if you use a Duffing wave, the spectrum will never be the same. Okay, only for random, like white noise. White noise is linear summation. It would be the same. I should make it more clear. Perhaps I totally confuse you people. They are very similar. Let me modify. They are very similar if the process is linear stationary. Okay? I have to change it. I have to change it. When you see this posted on the web, it will be different. Okay. All right. Without the question, class is dismissed. Bye-bye. Oh, by the way, I have an announcement. Friday, make sure you show up. Friday we'll have a very famous, world-renowned scientist from Arizona State University. His specialty is imaging terrain surface modeling. Yeah. So it will be extremely interesting to you. So be sure to show up Friday. If there will be a roll call, that will be Friday.
You have give us the second homework. What was the date?
It's the same date.
Only 1 week.
No, today is what? This next Friday. Yeah. Because you can ask extra questions, you should have slightly extra work. Okay? All right. Thank you very much. Bye-bye.